Hello everyone, I'm Zhao Jiadong. My student ID is DSC2509060. We are group 13. Group number group members is Zhengzimu DSC2509064 and He Qian DSC2509013 and Huang Shilong DSC2509017. So I will introduction the part 1 to you. Our project studies a sportswear factory producing basketball jerseys and shoes. They share equipment and materials, so their outputs affect each other. Management wants to know how many jerseys and shoes per week to mix this profit. There is a multi-variable optimization problem solved using calculus tool. So let's make a define. We define X equal to weekly jerseys production and Y equal to weekly shoe production. And revenue price drop with higher output. Jersey price 80 subtract 0.15x and shoes price 150 subtract 0.25y. So Rxy equal to this. Cost, let's define cost. Cost fixed cost 3,000 a week. Unit costs jerseys 40 and shoes 70. Cross term 0.06 SY for shared resources, and this CXY. So our profit is PXY is here. There's our objective function.
Hello everyone, my name is Zhengzimu and my student ID is DSC2509064. Today I will show you how to find the best production mix to get the maximum profit. First, let's start at slide 4. Here we use the first order partial derivatives to find our target production numbers. In our profit function, X is jerseys and Y is shoes. To find the highest profit point, we set both partial derivatives to 0. This gives us two simple formulas. Partial p divided by partial x equals to negative 0.3x minus 0.06y plus 40 equals to 0. Partial p divided by partial y equals to negative 0.06x minus 0.5y plus 80 equals to 0. To solve them easily, we change the decimals into whole numbers. This gives us 30x plus 6y equals to 4,000 and 6x plus 50y equals to 8,000. After solving these two equations, we get the unique result. The best output for jerseys is about 104 units. The best output for shoes is about 148 units. Now let's move to slide 5. We need to double check if these numbers really give us the maximum profit. To prove this, we use the second order derivative test, which is also named the Hessian matrix test. From our second derivatives, we get three key numbers. fxx equals to negative 0.3, fyy equals to negative 0.5, and fxy equals to negative 0.06. Next, we calculate the determinant d using the formula on the screen. So, after using this function, we can easily get d is 0.1464, which is greater than 0. So, because d is greater than 0 and fxx is less than 0, the matrix is negative definite. In simple words, this mathematically proves that this function will bring the company the highest possible profit. So our final strategy is clear. Produce 104 jerseys and 148 shoes. Thank you. That's all for my part.
Hello everyone. Now I will present the calculation result of our optimization model. After solving the partial derivative equations, we obtain the optimal production plan. The company should produce approximately 104 jerseys and 148 pairs of shoes every week. At this production level, the company can achieve the maximum weekly profit of 4,978.14 ringgit. These values represent the critical point of our profit function. According to the Hazen test, the critical point is confirmed to be the maximum point, which means this production plan gives the highest possible weekly profit. Besides the maximizing profit, this plan also helps the company allocate its production resources more efficiently and avoid unnecessary production costs. Next, let's look at the result analysis. First, the 3D surface graph shows how profit change as the production quantities of jerseys and shoes increase. As the production approaches the optimal point, profit continues to increase. However, after passing the optimal point, profit begins to decrease because the production costs grow faster than revenue. The contour plot also supports this result. The red point in the center represents the optimal production combination, which is approximately 104 jerseys and 148 pairs of shoes. The comparison table further proved our conclusion. When production is 90 jerseys and 130 shoes, the profit is 4,789 ringgit. When the production reaches 104 jerseys and 148 shoes, the profit increased to 4,978 ringgit, which is the highest value. If production continues to increase to the 110 jerseys and 155 shoes, the profit decrease again. Therefore, our optimism result is reliable. Finally, based on our analysis, we recommend that the company produce approximately 104 jerseys and 148 pairs of shoes every week. This production strategy allows the company to maximize its weekly profit while maintaining efficient use of production resources. Although our model is useful, it still has some limitations. For example, we assume that market demand, production costs, and selling price remain constant. In reality, this factor may change due to competition, customer preference, or economic conditions. In the future work, more variables such as labor costs, seasonal demand, and inventory management could be included to make the model more realistic and accurate. That's all of my part. Thanks for listening.
Hello everyone, my name is Huang Shilong. My student ID is BSC2509017. This is slide 8. Practical meaning. According to our profit function, the maximum profit occurs when x is approximately 103.83 and y is approximately 147.54. Since x represents the number of joints product each week and y represents the number of pairs of sports shoes product each week, we wrote these values to practical whole numbers. This means the company should produce about 104 joints and 148 pairs of sports shoes per week. At this production level, the maximum profit is about 4,078 yuan per week. This result has a clear business meaning. The company should produce more sports shoes than joints. In our model, sports shoes has a higher selling price and stronger profit potential. However, producing more product doesn't always mean earning more profit. when production keeps increasing, the selling price may decrease because of the market competition. At the same time, production cost, inventory cost, and management costs may also increase. Therefore, the best decision is not simply to produce as much as possible. The best decision is to find a balance as possible. The best decision is find a balance between jeans and sports shoes. This is where partition diagrams are useful, because they help the business find a production plan that gives the highest profit. Next, slide 9. Limitations and improvements. Although the model is useful, it also has some limitation. First, this is a simplified mathematical model. In real life, mathematical diamond may not follow the exact price function we used. The price and the demand for jeans and sports shoes can change because of sports seasons, fashion trends, school events, and competitions. Second, the model should not include practical constraints. For example, a real company may have limited budget, limited storage space, limited workers, or supply limits. These constraints may prevent the company from producing exactly 104 jeans and 148 pairs of sports shoes every week. Third, the model uses assumed data. It is useful for showing the method, but a real sports business should use actual sales data and cost data. To improve the model, the company can collect real business data and update the function regularly. It can also add changes such as budget, labor hours, storage space, and production capacity. If constraints are included, we can use language multiples to solve the optimization problem. The company can also use sensitivity analysis. This means testing how the optimal decision changes when price, cost, or demand change. Overall, this project shows that Character 2 is not only about formula, it can also help business make better decisions about production, pricing, and profit.
To summarize, we use the multi-variable calculus to determine that the optimal weekly production of basketball jerseys and shoes that maximize the profits. Our model shows that producing 104 jerseys and 168 pairs of shoes gives the highest weekly profit of about 4,968 yuan. This approach can help real business make better production decisions. Of course, this model has limitations such as ignoring the demand fluctuations and product interactions, but it provides a solid starting point. Thank you for watching.